Welcome back. Today's video covers the basics of riflescopes, how they work, first versus second focal planes, parallax, MOA versus MRAD, types of reticles, how to use your reticle to measure distances, how to check that your reticle is tracking correctly as you change elevation, and best practices for using your dials and cleaning your lenses. This video will not review the many options available for installing, sighting in, or leveling your scope. Let us know in the comments if you would like us to do a video on these topics. For us, it suffices to do an initial bore sighting and then fine-tune on paper. When it comes to the quality of a riflescope, it's primarily about the lenses. Lenses work by bending light, a process called refraction, as light reflected off a target passes through them. There are two common lenses to talk about in riflescopes: convex lenses, which are thicker in the middle and cause light rays to converge on a focal point, and concave lenses, which are thinner in the middle and cause light rays to diverge or spread out. Convex lenses handle the magnification aspect of riflescopes, but magnification comes with distortions that the concave lenses help to minimize. Chromatic aberrations are a color fringing effect on the target's edges, and spherical aberrations are a blurring effect on the target's edges. Lens coatings also help to minimize aberrations, as well as the dimming inherent in multi-lens assemblies. Coatings increase light transmission, reduce glare, enhance sharpness and contrast, and improve color fidelity by minimizing chromatic distortion. Coatings are important for protecting outer lens surfaces from abrasion and moisture as well. Coatings include magnesium fluoride, zinc sulfide, zirconium oxide, and many proprietary blends. The higher the number of coatings, the more expensive the scopes tend to be. Coated lens assemblies have at least one layer of coating on at least one lens surface. Fully coated assemblies have at least one coating layer on all lens surfaces. Multi-coated assemblies have multiple coatings on some but not all lenses. And fully multi-coated assemblies have multiple coatings on all lens surfaces. There are three key groups of lenses within the scope's tube to talk about: objective, erector, and ocular. The objective assembly collects ambient light and converges it to the first focal point where the image becomes inverted. The greater the diameter of the objective, the more light enters the scope, providing better vision in low light. Past the first focal point, light diverges on its way to the erector assembly, housed within a secondary inner tube. There are two sections to the erector assembly that can move in relation to each other. Moving the sections closer to or further from each other changes image magnification, with longer tubes permitting greater magnification. Scopes are labeled by their range of magnification followed by the objective diameter in millimeters, for example, 2 to 10 by 42. The erector tube as a whole is also moved by means of threaded screws, up or down for elevation, and left or right for windage. Past the erector assembly, like the objective assembly, light converges to a second focal point where the image is again inverted. After the second focal point, light again diverges on its way to the last assembly, the ocular. An adjustable ocular ring permits shooters to focus the reticle to their eye and has its own focal point. The closer this focal point is to the lens, the closer the shooter's eye needs to be to the eyepiece to focus properly. This can create a hazard when shooting in high recoil situations. Systems with an ocular focal point further from the eyepiece are considered more forgiving, providing greater eye relief. The diameter of light leaving the ocular is called the exit pupil, with larger diameters giving your eye more light to see. To calculate the exit pupil of your scope at a given magnification, divide the objective lens diameter in millimeter by the magnification factor. Higher magnification results in less light reaching your eye, while lower magnification permits a brighter and more clear image. The human pupil is limited in dilation to about 7 millimeters, so trying to achieve an exit pupil larger than that is unnecessary. Reticles come in two flavors depending on whether they're located at the front or back end of the erector assembly. First focal plane scopes have the reticle at the front end. Second focal plane scopes have the reticle at the back end. Because a first focal reticle resides ahead of the erector assembly, line thicknesses and the distances between lines change with magnification. so reticle dimensions change proportionally with target dimensions and can be used to gauge target size and distance. A second focal reticle, being located behind the erector assembly, is unchanged by magnification, so the value of line thicknesses and the distance between lines changes as target size changes. Measurements can only be made by knowing the value of those lines at a given magnification. For these reasons, first focal plane scopes are preferred by long-range and tactical shooters who constantly use their reticles to measure and adjust their hold, while shorter-range hunters often prefer the thicker reticle, which can be an advantage in low-light conditions. Reticle markings are specifically made with each line and distance between lines indicating a measurement in MOA or MRAD, a feature called subtension. Subtension in general means the area or distance covered by something at a given distance. In the case of rifle scopes, subtension refers to the angular size a reticle mark covers in MOA, minutes of angle, or MRAD, milliradians. A minute of angle is an angular measurement equal to 1/60th of 1 degree in a 360-degree circle. 1 minute at 100 yards is roughly 1 inch, well, actually 1.047. Adding another inch each 100 yards, a good rough estimate, but at 1,000 yards, 1 minute is 10.468 inches. A milliradian is another angular measurement equal to 1/1000th of a radian in a 6.2832 radian circle. 1 mil at 100 yards is roughly 10 centimeters, or 3.6 inches. Well, actually 100 meters rather than 100 yards. Like minutes, mils increase proportionally with distance to target. 1 mil is 3.6 inches at 100 yards, 7.2 inches at 200 yards, and so forth. For the reasons mentioned previously, subtensions remain consistent despite magnification level in first focal plane scopes, enabling measurements. To measure distance using a first focal plane reticle, the following formulas are used with a target of known size. The MOA formula: distance in yards equals target size in inches times 95.5 divided by target size in MOA. Lots of folks use 100 instead of 95.5 here for easier math in the field. The mil formula for distance in yards equals target size in inches times 27.77 divided by target size in MRAD. The mil formula for distance in meters equals target size in centimeters times 10 divided by target size in MRAD. Conversely, use the following formulas to measure target size when the distance is known. The MOA formula: target size in inches equals distance in yards times target size in MOA divided by 95.5. The mil formula: target size in inches equals distance in yards times target size in MRAD divided by 27.77. Second focal plane scopes can be used for measuring as well, but are only accurate at a specific magnification, where the reticle is calibrated to target size, typically at maximum magnification. The last major optical feature to discuss is parallax. Parallax is the apparent movement of the reticle across the target when you move your head, caused by the images of the reticle and target not being in the same focal plane. When those images are in the same focal plane, both are equally focused and the reticle doesn't move when you move your head. First focal plane scopes typically have a parallax adjustment knob or side focus on the left side of the scope tube. To adjust parallax, first make sure your reticle is in focus by using the ocular ring. Then move the parallax knob until your target is also in focus, and double-check by moving your head to see that the reticle stays fixed on target. Some scopes use an adjustable objective rather than a parallax knob for this purpose. It's important to note that although parallax knobs come with yardage markings, these are only intended as a very rough starting point. Second focal plane scopes typically don't offer adjustable parallax, but rather are fixed parallax. They are parallax-free at a set distance, typically 50 yards for rimfire scopes, and 100 to 150 yards for centerfire scopes. Aside from higher quality lenses, larger, longer tubes, more adjustment features, taller elevation turrets with click stops, and fancy illuminated reticles with built-in electronic leveling systems, what else are we paying for in a higher-end scope? Answer: a scope that won't fail you in harsh conditions. That means creating a sturdy scope that won't allow water or dust to enter the tube, and that eliminates any moisture that does manage to make its way in. Two methods are used to achieve that environment: physical sealing and gas purging. Physical sealing is done with O-rings to create a tight seal around the lenses and knobs. Gas purging is done after sealing, using a dry inert gas, such as nitrogen or argon, to displace ambient air and reduce the risk of fogging due to condensation. Argon is more expensive, but is preferred over nitrogen for its higher density and stability. A scope that is waterproof isn't necessarily fog-proof unless gas purging has been done. Additionally, you can help maintain the health of your scope by using desiccant packets during storage and travel, covering your scope with an insulated case, and cleaning regularly with eyeglass cleaner or isopropyl alcohol. Do not use Hoppy's No. 9 on your lenses, as this will strip the coatings right off. There are some best practices when it comes to handling your rifle scope. Perhaps the most important, and most often neglected, is returning your elevation and windage dials to 0. Many a shooter, us included, has forgotten to dial back down after hitting steel at 1,000 yards, only to wonder why we can't hit anything at 100. This also becomes a safety issue when turning toward a smaller berm to shoot at a shorter distance. And when it comes to dials, try to hold windage with your reticle rather than turning the knob. Wind changes a lot faster than elevation, so getting comfortable with using the reticle allows for much faster adjustments. Also, protect your scope from getting jostled during transport or crammed up against other rifles in your safe. And buy decent quality scope caps that fit well to protect those expensive lenses. Pro tip: position your objective and ocular scope caps such that they don't block your view of your target or your turret, and don't interfere with your bolt. Lastly, how do you troubleshoot your scope when impacts aren't where you thought they should be, particularly at long range?
Did you see that?
Did not.
Impact was over the log, about half a target high on the right edge.
Having ruled out shooter error, the quality of the cartridge, the bedding of the rifle, and the solidity of the scope mount, a method called the tall target test is used to see if your reticle is tracking properly as you dial your elevation up. Make a target with an aim point at the bottom and a line extending straight upward, placed 100 yards from your muzzle. Since different rangefinders often produce different readings, it's best to use a measuring tape to place your target. Use a level to set up your target and on your scope to make sure your reticle is not canted to run the test. Start with a 3 to 5 shot group at the bottom aim point to confirm your 0 at 100 yards. Then dial your turret up 30 MOA or 10 MRAD and shoot another group, holding the same aim point as the first. Measure the actual point of impact shift between the two groups. Then calculate the expected point of impact shift, which equals distance in yards times dialed elevation times a constant. For yards and MOA, that constant is 0.01047. So if you've shot at 92.66 yards and dialed your elevation up 30 MOA, multiply 92.66 times 30 times 0.01047 to get an expected shift of 29.1. If you've shot an actual shift of 29, to calculate the correction factor for your scope, divide the expected point of impact by the actual point of impact shift. So in this example, 29.1 divided by 29 gives you a correction factor of 1.003, which is a 0.3% error for the scope in this example. Many shooters, particularly at shorter distances, don't worry about the point of impact shift unless it's over 1%. For correction factors greater than 1%, simply multiply the elevation you theoretically need by the correction factor to get the elevation you actually need to dial on your scope. The tall target test can also show if your windage is shifting as you turn your turret up. On the same target, observe if your point of impact is shifted left or right of midline from your original point of aim. If it has, it's a simple matter of re-leveling your scope on its longitudinal axis until the vertical stays true. If your scope simply won't behave, it may be time to take advantage of the manufacturer's warranty. We've never had a problem with our local Leopold facility repairing or replacing our scopes, no matter how old. Whatever rifle scope you choose, be sure to focus on your fundamentals to take full advantage of it. Good trigger control, positive cheek weld, stable platform, and keeping your reticle vertical are all critical components. Most of the time we have issues, it's because we've neglected one of these primary factors. And making good wind calls. See you in our next video, and thanks for watching.
Center plate.
That's a good sound. That's a good sound.